Hey everyone, welcome back to Chem.03. Today, we're talking about something really fundamental in organic chemistry, how bonds actually break and form. Every single time a reaction takes place, some bonds are broken and new ones are made. But have you ever stopped to think about how that actually happens? Understanding what's going on at the molecular level when bonds form or break is the key to really getting how reaction mechanisms work. So let's dive in and break it down together. Every chemical reaction is a transformation, where reactants turn into products. And for that to happen, some bonds have to break and new ones have to form. Now, how those bonds break and form, that's what gives us a window into the reaction mechanism. The mechanism tells us what's happening, step by step, at the atomic level, including the exact order of events and how fast each step takes place. Let's start with how bonds form. There are two main ways this can happen, either symmetrically or unsymmetrically. In symmetrical bond formation, each atom contributes one electron to form a covalent bond. When we draw it out, we use single-headed curved arrows to show how those unpaired electrons move. A classic example of symmetrical bond formation is radical coupling, when two radicals come together to form a sigma bond. Each radical donates its unpaired electron, and just like that, a strong new bond forms. If you take a look at the reaction diagram, you'll see two dots representing the radicals moving toward each other, and those single-headed curved arrows, they show exactly how the unpaired electrons come together to form a bond. This kind of process is super common in radical reactions and in polymerization, where small reactive species link up to build bigger molecules. You can also see this in cyclic systems, where radicals at specific positions in a ring combine to form a new sigma bond. That new bond is usually shown as a yellow line in the diagram, highlighting the connection that helps stabilize the whole molecule. Alright, now let's move on to unsymmetrical bond formation. This happens when one atom donates a full pair of electrons to another atom, usually one that's electron deficient. It's a key feature of polar reactions, where you've got an electron-rich species interacting with an electron-poor one. And when we draw these mechanisms, we use double-headed curved arrows to show the movement of that electron pair. One of the clearest examples of unsymmetrical sigma bond formation is when a nucleophile reacts with a carbocation ion. The nucleophile, which has extra electrons, donates a full pair to the electron-deficient carbocation ion, and that forms a new sigma bond. If you look at the reaction diagram, you'll see a curved arrow showing that electron movement. It's basically an electron handshake. Another good example is when a pi bond acts as the electron donor in sigma bond formation. The electrons in that pi bond shift over toward a carbocation ion, and that creates a new sigma bond. In the diagram, the yellow bond highlights this newly formed connection, and this kind of step is a hallmark of electrophilic addition reactions. Next, let's talk about pi bond formation. You'll often see pi bonds forming or breaking when electrons move around in resonance structures. Now, just a heads up, some of the diagrams you'll see show hypothetical electron shifts, not actual reaction steps. A classic example is in carbonyl bond formation, where the oxygen donates its lone pair to form a double bond with carbon. Something similar happens in thiocarbonyl systems. You can also see this in cyanide compounds, where the lone pair on nitrogen shifts over to strengthen the triple bond, which helps stabilize the molecule. These kinds of electron shifts are super important in all sorts of organic transformations. Now let's talk about how bonds break. Just like bonds can form in different ways, they can break in different ways too, and the two main types are homolytic cleavage and heterolytic cleavage. In homolytic cleavage, or homolysis, the bond splits evenly. Each atom takes one electron from the bond, and that creates two neutral radicals. This type of bond breaking shows up a lot in reactions that are triggered by heat or light. If you check out the reaction diagram, you'll see single-headed curved arrows that show exactly how those electrons are moving. Sigma bond homolytic cleavage is a classic feature of radical reactions, like when a bromine molecule breaks apart into two bromine radicals. Another good example is with peroxides. When the OO bond breaks symmetrically, it forms two alkoxy radicals, and those radicals can go on to react further. In more complex systems, homolytic cleavage shows up in NBS, that's N-bromosuccinimide, where the weak NBr bond breaks and forms a bromine radical. That radical then jumps into allylic bromination reactions. You'll see something similar in nitrogen-based compounds like AIBN, azobisobutyronitrile, where bond cleavage produces radicals, and nitrogen gas is released in the process. That loss of nitrogen is what helps drive the radical formation forward. Understanding how all this works is a big part of getting the hang of free radical chemistry. Heterolytic cleavage, or heterolysis, works a little differently. Instead of each atom taking one electron, the entire electron pair moves to just one of the atoms. That means you end up with charged intermediates, like cations and anions. The more electronegative atom grabs the electron pair and becomes a negative ion, while the other one is left positively charged. When we draw this kind of electron movement, we use double-headed curved arrows to show that a full electron pair is being transferred. You'll see heterolytic cleavage in reactions like SN1 or E1, especially with tertiary alcohol halides. In these cases, the halogen just leaves, and that generates a carbocation intermediate. A similar thing happens under acidic conditions. Alcohols or ethers get protonated first, and that makes it easier for the leaving group to go, leading to carbocation formation through heterolytic cleavage. Pi bond cleavage follows a similar pattern. In carbonyl compounds, electron pair movement can break the pi bond and lead to ionic intermediates. You'll also see this in cyanide systems, where the triple bond can break unevenly and create charged species. These kinds of processes are at the heart of many organic reactions, like nucleophilic additions and eliminations. At the end of the day, bond formation and cleavage are at the core of every chemical reaction. Whether we're talking about radical or polar reactions, the way bonds break and form determines how molecules interact and transform. And once you understand these fundamental ideas, it becomes way easier to tackle more complex reaction mechanisms down the road. All right, that's it for today's lesson. Thanks for watching, and I'll see you in the next one.